BAS 202 Engineering Chemistry Most Important Questions Unit 3 Electrochemistry Question 1. What is lead storage battery given its construction and working? Answer. Lead storage battery. 1. Lead storage battery or lead acid battery is the oldest type of rechargeable battery and one of the common energy storage devices. 2. In these batteries, electrodes and electrolytes are altered by chemical action that takes place when cell delivers the current, which can be restored by forcing current through them. 3. The batteries used in automobiles, for example, in cars, buses, trucks, etc., are lead storage batteries. Construction. 1. The cell consists of a lead grid filled with a spongy lead as anode and a lead grid packed with lead oxide as cathode. Second, a solution of H2SO4 38% by mass is used as an electrolyte. Third, this is the battery acid which one can buy at service stations. Fourth, the battery consists of 6 such cells connected in series, each cell having an EMF of about 2 volt, giving 12 volt as the overall EMF of the battery. Working, discharging. First, when the battery is discharging, i.e., when it is supplying a current, the reactions are at anode, at cathode, the overall reaction during discharge. Second, the electrolyte is sulfuric acid H2SO4, which is gradually used up. Third, both electrodes become coated with an insoluble layer of lead sulfate, which, being an insulator, would eventually ruin the battery. Fourth, as the battery provides energy, it is discharged, and this leads to the gradual formation of lead sulfate at the electrodes and a steady decrease in the concentration of the sulfuric acid. Fifth, if the battery is totally discharged, both electrodes will have been converted to lead sulfate. Charging. 1. When the battery is being charged, electrons are supplied to the anode of the battery and this converts the lead sulfate to lead. 2. At the same time, the lead sulfate at the anode is converted to lead dioxide. 3. That is the cell reactions are reversed and the cell operates like an electrolyte cell. 4. The reactions are. Fifth, the concentration of H2SO4 decreases during discharging whereas it increases during charging. 6. The lead storage cell is both a voltaic cell and an electrolytic cell. 7. When electricity is being drawn from the cell to start the car, it acts as voltaic cell. Question number 2. What is electrochemical corrosion? Write down the mechanism involved in electrochemical corrosion. Answer. A. Electrochemical or wet corrosion. 1. Corrosion is the process of gradual deterioration of a metal from its surface due to the unwanted chemical or electrochemical interaction of metal with its environment. 2. For example, A. Formation of a layer of reddish scale of hydrated ferric oxide on the surface of iron, also known as rusting of iron. B. Formation of a layer of black coating on the surface of silver when it is exposed to atmosphere. It is known as tarnishing of silver. B. Mechanism of electrochemical or wet corrosion. The corrosion of metals in aqueous medium seems to be the electrochemical in nature. This type of corrosion is also known as immersed corrosion and generally takes place when, first, a metal is in contact with the moist air or any liquid medium, or 2. When two different metals or an alloy is in contact with a solution. First, electrochemical corrosion involves A. Separate anodic and cathodic areas between which current flows through the conducting medium. B. Non-metallic ions like O or O2 are formed at cathodic areas. C. Occurrence of oxidation corrosion at anodic areas which generates metallic ions. D. Diffusion of metallic and non-metallic ions towards each other through conducting medium results in the formation of corrosion product somewhere between anodic and cathodic areas. 2. For example, rusting of iron in neutral aqueous solution of electrolyte. In the presence of oxygen or in acidic environment with the evolution of hydrogen. Third, the corrosion takes place as discussed below. A. Anodic reactions. At anodic area, oxidation reaction takes place where metal atoms lose their electrons to the environment and pass into the solution. Thus metal is destroyed by dissolving or changing into metallic ions. Hence, corrosion takes place at anodic areas or metal, which forms the anode, is corroded. B. Cathodic reactions. The electrons released in the anodic reactions are consumed in the reactions at the cathode or cathodic reactions. Depending upon the nature of the corrosive environment, cathodic reactions may result in 1 cent oxygen absorption in presence of dissolved oxygen I. In acidic medium, 2. In neutral or weak alkaline medium. Second, hydrogen evolution, in absence of O1. In acidic medium, 2. In neutral or alkaline medium. Third, electroplating, at the cathode, metal ions collect the electrons and get deposited on the cathode surface. Question number 3. Explain different cause of deterioration in the cement and how to prevent it. Answer A. Alkali-silica reaction. Alkali aggregate reaction. First, Portland cement contains very alkaline ingredients such as Na2+ and K+, which in presence of water create a high alkali environment. Second, if the aggregates contain reactive silicates, these silicates react with the alkali and produce ASR gel. Third, ASR gel in presence of moisture can swell and cause tensile stress throughout the concrete core, which results in cracks and deterioration. Prevention. First, incorporation of non-reactive aggregates, low alkali Portland cement, and supplementary cementitious materials SCMs are the 3 effective solutions to prevent ASR in concrete structures. B. Alkali carbonate reaction. ACR. First, ACR occurs when certain types of dolomitic limestone aggregates are used in concrete in the presence of high alkali Portland cement. The products of this reaction are also expansive like ASR gel and cause deterioration of concrete. Prevention. First, to protect structures from carbonation distress, all the exposed concrete surfaces need to be coated to reduce the rate of penetration. Second, in addition, incorporation of supplementary cementitious materials such as fly ash, slag and silica fume enhances the density and quality of the concrete and prevents penetration in new concrete. C. Corrosion. First, in the presence of high alkali ions in concrete S solution results in high pH of the concrete. The steel reinforcement inside the concrete passivates itself by forming a passive layer at the steel reinforcement. Second, this passive layer protects the reinforcement from chloride attack and corrosion. Once the pH of the concrete decreases, the concrete matrix is no longer in the alkali condition and the passive layer at the reinforcement is destroyed. Third, the existing reinforcement is now exposed to aggressive chemicals such as chloride ions. As soon as the chloride content at the level of reinforcement steel exceeds the threshold, the corrosion of the reinforcement is propagated and deteriorates concrete. Prevention. First, to protect concrete structures from chloride attack, the top surface of the concrete slabs needs to be coated properly to decrease the penetration of chloride ions. D. Sulfate attack. First, one of the components of the hydrated Portland cement is calcium sulfoaluminate. Second, the source for formation of this component is gypsum, which is usually added to the Portland cement to control the setting time of the concrete. Third, The formation of this component is an expansive process and occupies more space, which cases international tensile pressure. Fourth, sulfates from external sources like water or soil penetrate the concrete and react with monosulfate, which is one of the cement as hydration products, and form calcium sulfoaluminate, which expands and cause damages. Prevention.
First, the most effective ways to prevent sulfate attack in new structures are using high-quality concrete with low water-to-cement ratio and or SCM content. Delayed ettringite formation definite. First, the other common form of sulfate attack is called delayed ettringite formation definite, which is more common in precast concrete manufacturing. Second, unlike the sulfate attack mentioned above where the source of the reaction is external sulfate from soil or water. Third, the sulfate source for definite is internal, and no external source of sulfate is required to trigger the reaction. Fourth, at high exposure temperature the sulfate ions form the existing ettringite are released into the concrete matrix. Fifth, these released sulfates, which react with the hydration products of Portland cement
and form secondary ettringite. Sixth, as mentioned above, when the concrete is hard, any formation of ettringite causes internal pressure and distresses. Prevention. First, the effective ways to prevent definite damages in precast elements are limiting the exposure temperature during the curing process to prevent ettringite as decomposition, as well as using an air entraining agent in concrete to create voids for secondary ettringite to accumulate. Acid attack. First, two main components of Portland cement are calcium silicate hydrate CSH gel and calcium hydroxide CaO2. Second, CSH gel occupied most of the paste matrix and is responsible for concrete as mechanical and durability properties. Third, calcium hydroxide occupies approximately 25% of the concrete paste volume and is not as effective as CSH to provide strength for concrete. Fourth, the alkali ions from Portland cement along with the calcium hydroxide are the reasons for high pH of the concrete materials. Fifth, external concentrated acids penetrate the concrete, react with calcium hydroxide, and form salt and water, which can leach out from the surface of the concrete and negatively affect both the mechanical and durability properties of concrete. Prevention. First, incorporation of SCMs enhances the quality of concrete and consequently prevents the acid attack. Salt attack. 1 SR. Salt attack occurs when the exterior surface of the concrete structure is exposed to water that contains salt. Once the water evaporates, salt remains on the surface of the concrete and causes pressure and damage. Prevention. First, applying sealer to the face of the concrete and using high-quality concrete can mitigate salt attack. Question number 4. What are corrosion inhibitors? Explain the mechanism of their action. Answer. A. Corrosion inhibitors. First, corrosion inhibitors are the substances which, when added in small quantities to the corrosive environments, decrease the corrosion rate. Second, inhibitors are organic as well as inorganic substances that dissolve in the corroding medium. Third, inhibitors are generally classified on the basis of electrode at which their action is predominant. B. Type of inhibitors. First, anodic inhibitors. First, the anodic reaction takes place when the ions from the anodic metal pass into the solution, for example, Fe2++2e. Second, the anodic inhibitors are the compounds which react with these metal ions to produce insoluble compounds. Third, this insoluble compound get adsorbed on the metal surface, forming a film or a protective barrier, thereby reducing the corrosion rate. Fourth, examples: A. Molybdates, phosphates and chromates of alkali and transition elements. B. Substances like Na2, Cro4, Nano 2, act as anodic inhibitors by forming less soluble compounds with the anodic metal ions. C. The organic compounds can also act as anodic inhibitors, and example include sodium benzoate. Second. Cathodic inhibitors. First. The cathodic reaction in acidic medium is represented by 2H++ 2EH. Second. Thus, corrosion can be controlled by slowing down the diffusion of H ions to the cathode. Third. The diffusion of H+ ions is considerably reduced by organic inhibitors such as amines, mercaptans, heavy metal soaps, substituted ureas and thioureas. Fourth, these substances are capable of being adsorbed at the metal surfaces and thus restrict the diffusion of H+ ions. Fifth, antimony or arsenic oxides are used as cathodic inhibitors because of the formation of adherent film on the surface of the metal. Sixth, compared to anodic inhibitors, cathodic inhibitors are quite safe. Seventh, this is because, even if they are used in concentrations less than required for complete protection, the partially covered cathodic sites decrease the surface of the cathode, whereas anodic area remains practically the same. Thus, corrosion decreases due to area effect. Third, vapor phase inhibitors. First, these are the inhibitors which readily vaporize and form a protective layer of inhibitor on the metal surface. Second, vapor phase inhibitors VPI are used to prevent corrosion in enclosed spaces and also during storage, packing, shipping, etc. Third, small metals are protected from corrosion by keeping them in the envelopes made from paper impregnated with a suitable vapor phase inhibitor. Fourth, dicyclohexylammonium nitrile and cyclohexylamine carbonate are amongst the most widely used VPIs. Question number 5. This question is most important for second semester. Question number 5. Discuss the electrochemical theory of corrosion along with equations. Explain why sheets of zinc metal are hung around the ship hull of ocean-going ships. Electrochemical theory of corrosion. Refer Q.2a. Cathodic protection or electrochemical protection. 1 cent. Cathodic protection is to force the metal to be protected to behave like a cathode, as a result of which it is not corroded. Cathodic protection can be achieved in two ways: A. Galvanic or sacrificial anodic protection. 1. In galvanic protection or sacrificial anodic protection, the metal structure to be protected is made the cathode by connecting it by a wire to a more anodic material. Second, as a result, the corrosion takes place at anodic material and the metal structure is saved from corrosion. Third, the more active metal used for the purpose is known as sacrificial anode. Fourth, the sacrificial anode is replaced by a fresh one when it gets corroded or consumed from time to time. Fifth, most commonly metals used for sacrificial anodic protection are Mg, Zn, Al and their alloys. Sixth, example Zn metal in ship. In ship, a sacrificial anode sheets of zinc metal is a anode, electrically linked to the ship metal cathode to be protected, that is more reactive to the surrounding corrosive environment. In this way, the sacrificial anode corrodes and protects the metal of the ship. Figure galvanic protection using sacrificial anode. B. Impressed current cathodic protection. First, this method, known as electrolytic method of cathodic protection, the object to be protected is made cathode by connecting it to negative terminal of DC source. Second, the positive terminal is connected to an insoluble anode like graphite, scrap iron or platinum. Third, the impressed current cathodic protection has been applied to protect A. Buried pipelines, transmission line towers. B. Water pipes, water tanks, marine piers, etc. Fourth, this kind of technique is particularly useful for large structures which require long-term applications. Fig. Impressed current cathodic protection. Second, anodic protection. First, anodic protection is applicable to the metals which can be passivated by the deposition of oxide films. Second, in anodic protection, oxide film is grown on the surface of the metal structure to be protected. Third, this is done by electrochemical means, i.e., by applying current in a direction that makes the metal structure more anodic. Fourth, under these conditions, the metal structure is passivated when the required potential is maintained and hence rate of corrosion decreases. Fifth, anodic protection has been applied in case of steel, stainless steel, aluminium and chromium. Sixth, it must be remembered that potential has to be accurately maintained so that it just induces passivity. Thank you for watching this video. Please subscribe this channel.